Hello, my name is Xiaoxiao Du, and I am presenting our recent work in unsupervised pedestrian pose prediction. We propose a deep predictive coding network-based approach, and we mainly focus on autonomous vehicle perception applications. The highlight of this work is that our proposed approach does not rely on manually defined models and distributions, but instead performs frame-based 2D pedestrian pose predictions based on future video generation. I will first describe what motivated this work, and then we will go into detail about our method. This slide shows a picture of an autonomous vehicle with mounted sensors on the left. We use this setup to collect the PEDX dataset at various intersections in downtown Ann Arbor. On the right is a sample image taken by the car-mounted camera containing multiple pedestrians walking on the right. For the autonomous vehicle to navigate safely in crowded areas, such as an urban intersection like this one, it is really important for the system to correctly understand and predict human poses, to be able to determine the intention of humans and make appropriate decisions so that the vehicle may act accordingly to avoid collision and ensure ride safety and quality. This slide shows the sample clip taken from the Joint Attention in Autonomous Driving (JAD) dataset that we use in our experiments. You will notice that the ego vehicle, that is, where the data collection camera was mounted, was moving forward in a parking lot, and there are several pedestrians walking by. The collected video contains both the self-motion of the ego vehicle and the motion of other objects, such as the pedestrians in the scene. Our task is to perform pedestrian pose prediction given such video sequences. In this work, the pedestrian poses were represented using a kinematic skeletal model with body joint locations, or key points. Given past video sequences, the goal of pose prediction is to capture the underlying motion model of humans and make inferences about pose and location of a person or persons at future time steps. One significant challenge that is often associated with standard supervised pose prediction methods is that they typically require accurate skeleton annotations of training sequences, which can be difficult and expensive to obtain. If prior annotations are imprecise, erroneous, or contain missing frames, the performance of supervised machine learning and deep learning methods may become worse. To address this problem, we developed an unsupervised method for pedestrian pose prediction. Our system builds upon the Deep Predictive Coding Network, or PredNet, as developed by Lauder, Cramen, and Cox in 2017. We use PredNet as an unsupervised video prediction module to generate future predicted frames, and then perform image-based pedestrian pose detection, which helps eliminate the need for accurate measurements and prior skeleton annotations for pedestrian poses, as were required by standard supervised pose prediction methods. Another challenge to this problem is that we're working on the pose prediction problem given only 2D monocular videos, without any additional data collection instruments such as a LiDAR. This setup can significantly reduce cost, but forego the accurate measurements and annotations for historic skeleton sequences that can be usually obtained by higher resolution and more expensive equipment. Additionally, as mentioned earlier, such traffic videos often contain multiple pedestrians simultaneously moving in the wild at various ranges of distance, and contain both self-motion of the ego vehicle and the motion of other objects in the scene. Here is a flowchart of our unsupervised pedestrian pose prediction pipeline, and we will go through each module in detail. First, the input of our pipeline is the raw RGB videos collected from a car-mounted camera. Note that prior annotation of poses is not required as input in this pipeline. Then, PredNet was used to generate future video frames. Here's an illustration for the architecture of the 4-layered PredNet that we're using. The green, blue, and red blocks represent the recurrent representation, R, prediction, A hat, input convolutional layer, A, and error representation, E, which are the 4 basic layered units. Given image sequences as input, the target value of the lowest layer is set to be equal to the image sequence. PredNet then goes through a top-down and bottom-up pass to calculate the states of all units in each layer, and gradient descent was used to minimize the overall error responses. We refer the audience to the original PredNet reference for the pseudocode and our paper for more detailed description of the algorithm. One thing we would like to point out is that our post-prediction network is based on, but not limited to, PredNet. In fact, the video prediction module shaded in yellow can be easily swapped with other video prediction methods. We favor PredNet in our system as it has demonstrated superior performance for future frame prediction with moving backgrounds, as shown in the original paper on the Kitty dataset and further validated in JAD and PEDEX datasets in this work. This fits our goal of predicting pedestrian poses from data as typically observed from an autonomous vehicle perception system. PredNet is an unsupervised method, which has the advantage of not requiring any annotation on skeleton or mesh of persons in a scene in prior sequences. Now let's go back to the full system illustration. After PredNet is used to predict pixel-level RGB values for the next frame given video input, poses were extracted using pre-trained human pose detectors based on predicted future frames. In our experiments, we used the OpenPose human key point detector to detect 25 2D key points of pedestrians based on the predicted future frames. To further filter out false alarms caused by non-human objects, another layer of human detector was applied to the OpenPose detection results. In our system, we applied a pre-trained mask RCNN to detect the human bounding box locations and thus filter out potential false detections. The final output of our pipeline is the predicted skeleton poses for pedestrians in future frames. Our pose prediction system generates future frames based solely on a car-mounted 2D monocular camera and performs direct pose estimation per frame, which no longer requires accurate measurements and annotations for historic skeleton sequences as required by prior supervised work. In addition, the PredNet module inherently incorporates implicit models of scene structures and movements of objects, such as buildings, streets, and pedestrians as observed from a moving vehicle. Moreover, previous supervised pose prediction methods often perform poorly with imprecise measurements or occluded body parts in previous frames. Yet our method naturally alleviates the missing data problem since our pose detector is performed per frame and does not rely on previous skeleton detection results. Here we will show some of our experimental results. We will present results on two real-world autonomous vehicle perception datasets, JAD and PEDEX. Table 1 presents a quantitative evaluation of frame prediction results on both datasets as compared to the actual collected video frames. As shown in Table 1, the PredNet module is effective in predicting the future frames. The lower MSE and higher SSIM in the PEDEX dataset can be attributed to the fact that the background seen in PEDEX is fixed, while the background changes with the motion of the car in the JAD dataset. Here we show a comparison of a sample video sequence from the JAD dataset and PredNet future frame prediction results on the right. The videos were downsampled to accommodate memory constraints. Note that the initial prediction is spatially uniform due to initialization, which is why in the right-hand side prediction video, there was a blank frame at the beginning of the sequence. We can observe that PredNet was able to produce realistic future frames and capture both the self-motion of the vehicle, as you see from the clouds in the sky, and the parked cars and stationary buildings, and the relative motion of the pedestrians walking in the scene. This slide shows the pose prediction results on a sample JAD video sequence. The left shows the ground truth poses, which were the open pose detection results from the original input frames. The right shows the predicted poses based on PredNet future frames. The poses were marked in open pose style skeletons with joint locations and limbs. As can be seen, this pipeline was able to detect and predict pedestrian poses quite well and capture the movements of the body parts, such as how the legs are moving within a gait cycle. This figure shows the predicted skeleton RMSE results of our proposed method in pixels. Each circle represents a key point or joint of the body. The colors of the circle represent the mean RMSE results across 3 runs. Yellow shows higher error and dark blue shows low error. The size of the circle represents the standard deviation value at each joint. The larger the circle, the higher the standard deviation. We observe from the illustration that the body center shows the lowest errors while the extremities show larger mean and standard deviation errors, which is understandable as the hands and feet are the most flexible parts of the human body and also most easily occluded, therefore the most difficult to predict. This slide shows the post-prediction results on a sample PEDX video sequence. Similar to previous results, the proposed approach was able to predict future frames and pedestrian poses quite well, and captures the motions of the scene and pedestrians. In PEDX, the blur effect seems slightly more prominent due to the fact that we used the PredNet model pre-trained on JAD, and the PEDX environment were not learned in training. Moreover, the spacing between frames were longer due to a lower frame rate in PEDX. However, such a blur effect did not seem to have significant impact on the post-prediction step, and we observed that our post-prediction module can still successfully detect the skeleton joint locations of pedestrians based on the predicted future frames. We present quantitative evaluation of root mean square errors of predicted poses by our proposed approach compared with baseline methods. We computed the RMSE in both width and height directions and mapped the pixel errors to bounding box size in metric space. As shown in the tables, we were able to achieve about 15 cm error in the x direction and 8 cm error in the y direction in the JAR dataset. On the PEDX dataset, since we trained on JAR dataset only and images from PEDX were never trained, the overall RMSE is slightly higher. Yet, we noticed from both the qualitative and quantitative results that the proposed approach can still predict reasonable poses with relatively small errors. Our approach is able to perform post-prediction for multiple time steps into the future. In our experiments, we have set the extrapolation time length to be 20 frames. After time step 10 in the MTP process, previous predictions were used as input to extrapolate future frames. We again show a sample clip of the predicted frames and poses using MTP. As time increases, the MTP model was still able to capture certain motions in the scene, such as the movements of the clouds and surrounding cars in the parking lot. However, the frame predictions will eventually become more and more blurry due to the accumulation of noise and uncertainty, which will cause inaccurate and missed post-detection results, such as the person on the right-hand side, in extrapolations further into a prediction horizon. Here are a few plots for evaluating the performance of multiple time-step predictions. We can observe that the frame errors were higher than next frame prediction results, and the MSE increased. SSIM and post-RMSE results decreased over time after the first 10 time steps. In the paper, we also provided discussions and analyses on computation time and some potential challenges with this method, such as its dependency on the accuracy of the frame-based human detector and some misdetections from lighting and other conditions. We invite the audience to further check out our manuscript and code for more details. In conclusion, we proposed an unsupervised pedestrian post-prediction pipeline based on a deep predictive coding network. Our system combines video generation approaches, such as PredNet, and frame-based pose detectors, such as OpenPose and MassRCNN, and shows effective future pose detection performance on real-world autonomous vehicle perception data. We hope that we have made some steps towards alleviating the heavy need of accurate annotations with abundant perception data, particularly in practical robotics and automation applications. Thank you very much for your attention.